guys, I'm recording this from the Comstock home, and I am going to start from the beginning of chapter 15. Even though we covered this in lecture the Friday before our extended spring break, it's been a difficult couple of weeks, and I wanted to give you an update. Okay, so first things first, I want you to understand Gibbs free energy, and I want you to be able to differentiate between anabolism and catabolism. In doing free energy calculations, we have these steady states, and we assume that for pure solids and liquids, the substance is actually pure, that gases have a pressure at 1 atmosphere, and all solutions have a concentration of 1 mole per liter. Assuming those standard states, we can calculate the delta G, or the Gibbs free energy, for any reaction using the formula below. And here you see delta G aught represents the delta G, or the Gibbs free energy, at equilibrium, and the regular delta G without the little zero circle above is the Gibbs free energy for a certain concentration of products and reactants. So looking at this formula again, you can see that the square brackets represent molar concentration, R is the gas constant, T is the absolute temperature in Kelvin, and Ln is the natural log. And I'm actually going to provide for you a couple of videos on Gibbs free energy. So I want you to look at those because they do a really good job of interpreting this and explaining how to calculate Gibbs free energy. And like I said before, the Gibbs free energy with the little circly thing above is called the delta G aught. And delta G aught is the Gibbs free energy when the reaction is at equilibrium. And so that means that your delta G for that reaction won't be moving forward or backwards, so your delta G is going to be 0, whereas your delta G aught can be calculated. And that's calculated based on the equilibrium constant, which is just a balance or the ratio of products to reactants. And this is going to be calculated experimentally. But again, I have some videos that go in and show you how to derive this, so it'll make a lot more sense. When free energy changes are calculated, they make this assumption that the hydrogen ion concentration is 1 molar. And that would mean that we'd have a pH of 0. And in biological samples, you do not have a pH of 0. We have a pH typically of 7.0, or 10 to the negative 7 molar. So we get this new little symbol here, which is delta G aught with that little line above it right there. I want you to go to your book and look at example 15.1. There's a few assumptions they make. First, that the reactions are carried out at a pH of 7 instead of a pH of 0, and at a temperature of 25 degrees Celsius, which is 298 Kelvin. And they use this to go and calculate the delta G aught for the hydrolysis of ATP. Then for this experiment, they give you the KQ, or the equilibrium constant for this reaction. And the equilibrium constant for this reaction is actually experimentally determined. And what scientists do here is they run these reactions, and then they measure the amount of products over the reactants. And that's what you see here. The products over reactants, KQ for that, is equal to 2.23 times 10 to the 5. Then using all these numbers, they show you how they calculate delta G aught. And delta G aught in this case is negative 30.5 kilojoules per mole, or if you use it in calories, they show you the conversion there. It's negative 7.29 kilocalories per mole. So I'm going to assign a couple problems at the end of this, and I want you to do these same types of calculations on your own. So using those calculations, we can look at all the reactions in the cell and see if they release or absorb energy in the process. So do they give off? Is the delta G negative, or do they require energy? Are they endergonic reactions, exergonic or endergonic reactions? And we already did the calculation here for ATP. ATP hydrolysis is an exergonic reaction. You have a energy produced from that process or released from that process is negative 30.5 kilojoules per mole. And what we find is that in living systems, we couple exergonic reactions to endergonic reactions. So to constantly drive what's occurring in the cell, we release energy from one process and use it to drive the next process. Metabolism is the sum of all the chemical reactions in the cell. And we have two types of metabolism, catabolism and anabolism. Catabolism is the breakdown of larger molecules into smaller ones, And anabolism is the buildup or making larger molecules from smaller ones. We see that catabolism is the breaking down of large biomolecules into smaller biomolecules. And we'll talk about oxidative and reductive reactions in the next PowerPoint. But catabolism is typically oxidative and energy releasing or exergonic. In contrast, anabolism takes smaller molecules and builds them up or synthesizes larger molecules. This is usually reductive and it requires an input of energy, so it's called endergonic. That's the end of chapter 15. I am assigning questions 10, 11, 12, and 14, and they will be due on Converge on Monday, March 30th, before class time. So by 11, because we're going to go over these problems on our Zoom conference call on Monday. All right, guys, that's it for the first part of chapter 15. I'll move on to the second PowerPoint soon.